Good morning, students. Welcome to online classes. On continuation of previous classes, today we are going to learn an interesting few more topics regarding to induction motor performance values with comparing to the our well known machine, that is transformer. Transformer, whether single phase or three phase transformer, and our three phase induction motor works based on same induction principles. In second year level, we are very familiar what is transformer, how it works, what are its characteristics, its equivalent circuit diagram and phasor diagram. We have seen clearly in last year classes. Same analysis we are going to adapt in our three phase induction motor, because transformer is a easy subject to our electrical students. By knowing that basic things, we are going to implement on our three phase induction motor to know the further its behavior. Let us see today what are the objects we are going to learn. On completion of this session, we are going to learn explanation of how an induction motor is treated as a generalized transformer. Second one, draw equivalent circuits as referred to stator, as well as if required we can write it in rotor side also. That is similar to the equivalent parameters referred to the primary side and the secondary side in case of our transformer. And finally, draw vector diagram with for phase values to know the what is its current and voltage, its phase angles between all things. At a glance, we are going to see the what is the performance of our induction motor. Now, let us see one by one. Do you know transformer has two windings called as a primary winding and secondary winding. Here the primary winding and secondary windings are stationary part. Basically, we know that transformer is a static machine that will transform energy from primary to secondary with same frequency, with changing its voltage and current correspondingly. Similarly, induction motor also have two windings. Those are stator, which is stationary part, rotor, which is rotating part. Now, in this case, we are comparing the primary winding of transformer similar to the stator of our induction motor. Secondary of transformer is compared with the rotor of induction motor. At the same time, as you know that transformer winding is concentrated winding, whereas our induction motor winding in stator as well as rotor, in case of slip ring induction rotor, both are distributed winding, 3-phase windings, whether it's a lap winding and wave winding. Only difference is this one. That's why same 3-phase transformer, 3-phase supply is given to the transformer. It produces a magnetic field, alternating magnetic field, which links with the secondary and induces a EMF in the secondary as per Faraday's laws of electromagnetic induction. But whereas same 3-phase supply is given to the stator of induction motor, it is also produce a magnetic field, but it is rotating in the air gap at a synchronous speed. This rotating synchronous field sweeps the rotor conductors. Due to the alternating in nature, it produces and induces an EMF in the rotor circuits, and which will produce its own magnetic field due to the stator magnetic field and rotor magnetic field. There is a torque is developed. Due to the torque, rotor will rotate in the same direction of rotating magnetic field. Whereas in transformers, there is no mechanical movement. In induction motor, there is a mechanical movement. So that's why we are going to electrical equivalent circuit compared with the mechanical circuit also. How can we compare that one? We will see in the next. Okay, so dear students, just whatever you studied about transformers, please recollect. If you know that basics, this topic is very easy to understand. Okay, so let us recall what we have seen. Okay, so in this class also, in induction motor also, we will see how the power which is given at stator side and transmitted to the shaft power. Okay, so let us before going to this one, so we will see its main parts. Please remember here what is happened. Please compare. This is a transformer. Transformer has core, okay, so it is a laminated, the laminations. Okay, similarly you can see, compare it. Similarly, we have the stator and stator core. It is also laminated similar to this one, and in this case I have used winding, copper winding, concentrated. I am seeing in the single phase here, at the same time 3-phase also, so it is maybe 3-phase also. Now here secondary winding, primary, that is called V1, secondary, that is called V terminal voltage. In between there is the magnetic core. Similarly, here 3-phase winding, so the winding is distributed in outer periphery of this core. Now, if the current which is flowing through this one, it produces its magnetic field that is flowing through this core and linked with the secondary winding. Then it induces EMF in secondary coil as per mutual induction, Faraday's laws of electromagnetic induction. Now, in this case, we have rotor. Rotor also has winding placed in bearings. Once the current supply is given to stator, it produces its magnetic field and it is rotating in the air gap between the stator and rotor, just like it is rotating at a synchronous speed. During this process, it also sweeps the rotor conductors and induces EMF in the rotor, and the rotor winding is closed position and it produces its own current and it produces its own flux. The flux induced such a way that it opposes cause of its production, that is the main relative speed between the rotor and rotating magnetic field. That is why rotor picks up its speed in the same direction of rotating magnetic field as we have covered in previous classes. Now, in this analysis we are going to this one. So, what is here? Now, how the power from the primary side power now we will see these all salient points in PowerPoint. So, dear students, I am going to compare our transformer analysis with our induction motor analysis. Okay, known to unknown we are going to learn. Now, let us what we have seen in previous classes. In this class, let us see the what are the salient points of these two topics. Okay. Now, here the transformer works on the basic principle of Faraday's laws of electromagnetic induction. Similarly, a three-phase induction motor also works with the same principle. The rotor windings of three-phase induction motor receives energy from the stator by means of induction. Therefore, its stator winding is directly connected to AC supply. You can see this figure. So, for example, this is the stator. So, this portion is the stator and is connected to the three-phase supply, and rotor is empty only. Okay, you can see it. Three-phase induction motor is a single excited machine. So, there is no DC business in this case. No excitation is required with the DC supply. Okay, so three-phase you can see here. Okay. Now, you can compare this with these values. Okay, this is a well-known three-phase induction motor, and this is a three-phase transformer. Okay, induction. This is the induction motor. This is the transformer. So here, what is happen? Three phases connected to the three-phase supply, and these windings are the concentrated windings, whereas these windings are the distributed. This is the concentrated winding secondary side. Okay. So, whenever the supply is given, it produces a magnetic field and rotate. The flux is flowing through the core and links with the secondary coils and induces EMF in the secondary sides. This is called self-induced in primary, self-induced EMF in the primary winding, and this is the mutually induced EMF in secondary. Similarly, so whatever the three-phase supply is given to the stator winding, it produces a magnetic field. That magnetic field is not in stationary similar to the transformer, but it is rotating at a speed of rotating magnetic field at a synchronous speed that try to induce EMF in the rotor conductors. Okay, so that already you have seen. It is possible to compare the operation of induction motor to that of transformer. The stator and the rotor of an induction motor can be compared to primary and the secondary of our transformer. Transfer of energy from stator to rotor of an induction motor takes place by induction principle. It is entirely inductively by the flux linking between the stator and rotor. Now, here what is the comparison? So, whatever the we learned in previous class. Okay. Now, next. In transformer, the frequency of primary and secondary is always same. Okay. So, what we have discussed in this class. So, here the transformer, whatever the transformer, this is equal to F, this is equal to F, this is equal to I1, this is equal to I2, this is equal to V1, this is equal to V2, this is equal to E1, this is equal to E2. Okay. Similarly, our winding, this is also, it is a primary 3-phase supply is given, and it is also winding, and this is equal to V1, and rotor induced EMF, this is equal to, we can say this is equal to V2, and the frequency of F, this is the frequency of F2 at standstill condition. The current I is flowing here, and we are going to find the rotor current also. Whatever the energy from the rotor stator side to rotor side in the form of magnetic field, that is the RMF. Magnetic field, here also whatever the field is the form of magnetic field, but it is flowing in the core, but it is rotating in the air gap at a speed of ns, synchronous speed, all similarity values. Under standstill condition, whatever the frequency of the stator is equal to the same frequency, and this rotating magnetic field sweeps the stator conductors also. Then, as per Faraday's laws of electromagnetic induction, it induces the EMF in stator conductors also. At the same time, this field induced EMF in the rotor conductors, that is equal to E2 under standstill condition. And similar to the E1, this is a E1, E2 and E2. What is the difference? Just we have seen that. What is that one? So, here the E1 of transformer is equal to 4.44 F, okay, flux into N1, and E2 that is equal to same 4.44 F 5 N2. In addition to, if this compared with our this one, so you are going to get it another component. That component is here K another component is the KW1 winding factor. Second is the winding factor of 2. So, this is the difference, that is equal to the same induced EMF in the primary is equal to 4.44 F5 N1 and KW1 in stator, and E2 induced EMF in the rotor is equal to 4.44 F5 N2 into KW2. This is the secondary. Whereas, a winding factor, that is the due to the distributed winding, whereas this is equal to 1 in case of our transformer. Okay, so that's why we can write it, what the equations we can write it, that is equal to, we can write it, so E1 is equal to of our so this is the induced EMF primary and induced EMF in the rotor. We can write the E2 at standstill condition. Okay. Now E1 is equal, I can write it, what is the formula, 4.44 F5 N1 into Kw1 winding factor, and so E2 we can write it 4.44 F5 and N2 Kw2 winding factor 2. So here E2 by E1 is equal to, we are going to get it. So what is the value? Just we are going to get this N2 by N1 into Kw2 by Kw1. So that is equal, we can say, is the transformation ratio similar to transformer. Okay. So similar, same thing here is the only due to the distributed winding. So we are going to get the winding factor Kw1 and Kw2 of stator and rotor respectively. Okay. Remaining are the same at standstill condition. If it is a running condition, what is happened? So here, so we can write it at standstill condition further all terms. In transformer, what is the transformer ratio? K transfer in transformer. So we can write it transformer K is equal, we can write it, what is the formula? V2 by V1 is equal to E2 by E1 is equal to N2 by N1 is equal to I1 by I2. Okay, this is the in transformer. In our condition, in induction motor, same K can be written as, so here what is that, just now we have seen, so what is the value? E2 by E1 is equal to N2 by N1 into that factor. What is the factor? That is a Kw winding factor by Kw1 at standstill condition. At the same time, we are going to observe that if our rotor rotates at the speed of n, then so we are going to get it. So here E1 is equal to induced EMF n and E2 is equal to rotor and E2 at standstill, what E2 induced EMF at standstill. Okay, standstill. But when it's at a speed of, that is equal, here slip is equal to 1. Now n, the ER is equal to, slip is not equal to the 1, it changes, then slip speed changes at a speed of R. Then we can say that, so ER 2 EMF induced in the rotor conductors at a slip speed, yes, that is, we can write it, that is equal S into E2. At the same time, what is the frequency? Frequency also FR2 rotor frequency at under running condition, that is equal S into F. So already we have seen this parameters of induction motor in previous classes. This under slip speed, under slip speed. So this is the, that is E is equal to, E2 is equal at standstill condition. Okay. Now let us see. Now what is the, this one? The frequency of the rotor EMF depends on slip speed, slip and the load on the motor. What is the slip speed? So as we know that slip speed is equal, already we have seen. What is the slip? S is equal to synchronous speed minus rotor speed divided by synchronous speed. Okay. So that is the slip, slip at standstill. at rotor speed and RMF, rotating magnetic field, and rotor speed, both are relative speed, that is the relative speed, rotating magnetic field and the rotor speed. If n is equal 0 at standstill condition, what is the S value? That becomes to the 1. S value becomes the 1. If ns and the rotor speed is equal to n is equal to ns at synchronous speed, then S value becomes to the 0. So our machine will operate from 1 to 0 slip under different load conditions. Okay. So whereas in case of the synchronous motors, the speed is constant, but whereas in induction motor, the speed will vary based on load on shaft. Hence the S also changes. If S changes, its a frequency, rotor frequency changes, and rotor induced EMF changes, and current also changes on rotor. We will see this all parameters. Okay. Now at starting, the slip of the induction motor S is equal 1. The frequency of supply of the stator and induced EMF in the rotor is same at standstill condition. Okay. And further, in the case of transformer, the entire energy present in the secondary circuit is in the electrical form. Okay. So what is the load on transformer? Is the electrical load, whether it is a tube light, whether it is a fan, whether it is a bulb, is a electrical loads only. But whereas in our induction motor, which type of the load is a mechanical load. So in induction motor, part of its energy in the rotor circuit is in the electrical form, and remaining part is converted into mechanical form. Okay. What is the electrical form? That's I square R losses, heat energy. Okay. So in general, induction motor can be treated as a generalized transformer. Now once you can see how this is a energy in the form of electrical energy, in the mechanical energy, we have seen in last class in different stages how the motor input takes place. From that one, how the stator and the rotor, some losses deducted. After that, the rotor input, that is a P2, and from that P2, so how the rotor copper loss is taken out. After that, there is a producing the total mechanical power developed in the rotor, that is a PM, or we can say the gross torque. And from that, so some of the losses, that is a windage and friction losses taken out. After that, we are going to get the rotor output in the form of BHP, brakes horsepower, in the form of mechanical energy. Okay. So last class we have discussed this all things. Okay. At a glance you can see here. So this is the induction motor. Okay. So what is happened? So when supply is given the terminals as electrical energy, and here you are going to get the mechanical energy. Okay. In between electrical to mechanical, there is a different type of the energy conversions takes place. Whereas in our transformer, you are going to give the electrical energy, you are going to get the electrical energy in output also. But whereas in our induction motor, in the form of electrical energy, we are going to the mechanical energy. In between, it is changing. So that means to entire electrical energy converted here. So in this case, electrical energy, some of the energy wasted in the form of I square electrical I square R, and remaining this is energy developed is a PM, mechanical power. Okay. Last class we have seen the power flows in a induction motor in different stages, and also we have done some few problems. Now you can see the flows. So here you can see it. Whatever the input is given here, that is the motor input in stator, that is called P1. We are given the direct supply is the P1 is given here. From this one, the stator has some stator core losses, and stator has winding, copper winding losses. So deduct these losses. The core losses depend on the voltage and frequency, and winding losses depend on the current and resistance. So whatever the total input minus these losses, we are going to get is a stator output or rotor input, that is considered P2. This rotor input P2 is utilized given to the rotor, and rotor also has its rotor winding and rotor core also, but the core of rotor depend on the frequency. So rotor frequency is equal, Fr is equal S times of F. So because under running condition the slip is very low, merely 2% to 3%. Hence we are neglecting these core losses while calculating in rotor circuit. So simply whatever the energy is given, that's we taken as a the copper losses in rotor, that is equal IR square R. From that is deducted here, and P2 minus this value, we are going to remaining energies given to the outside in the form of mechanical energy here. This is the mechanical energy. Up to this is the electrical energy. Whatever the input is given, up to it is electrical energy, or here up to electrical energy. But after that, here is developed the mechanical energy, torque, gross torque. From gross torque, some of the mechanical losses also we deducted, that is the windage and friction losses we taken out. From that we are going to the net rotor output, or that is a brakes horsepower is ready to take the mechanical load on shaft. Okay, these are the stages already we have seen in the previous classes. Okay, now coming to the further, here it is satisfied through the following relations. So we have seen already, if the supply is given to the stator 3-phase induction motor, according to the a rotating field is set up and EMFs are induced in stator E1 and rotor E2. So we have already derived this equation. E1 is equal to this value, so that is equal 4.44 kW1 the winding factor, the frequency 1 and N1 and phi 1, and secondly the E2 is equal to 4.44 kW2 winding factor, frequency 2, N2, phi 2. So these are the some equations in our induction motor, similar to the our transformer. Okay, so just you compare our known to unknown, dear students, don't confuse it. And further also we have seen that the Kw1 and Kw2 are the winding factors of stator and rotor windings respectively. So we have drawn the E1 by E2 is equal Kwny by Kw2. Okay, so this expression is similar to the voltage transformation ratio, E1 by E2 is equal to N1 by N2 of transformer, and there is a slight difference in the above equation. What is the difference? Can you tell it? What is the difference? So the use of distributed winding for the induction motor has compared to the concentrated coils used in transformer. There is no winding factor in transformers, and there is a winding factor in our induction motor due to the windings are distributed throughout the core material. Okay. Now this is a comparison between the our 3-phase transformer on 3-phase induction motors, primary and secondary, stator and rotor. Let us, so we have seen all these values. Let us conclude some few points to avoid the confusion. What are the main points regarding to our requirement comparison between the transformer and induction motor? Okay, so let us conclude it. An induction motor at standstill exhibits the same characteristics of a transformer on no load. In induction motor also, leakage fluxes as in transformer. Therefore, the operation of both devices is similar even under load conditions. The stator and rotor have winding resistance and leakage reactance as in transformer winding. So, because winding itself it has some resistance and it is the leakage reactance X2 and R2 values. Transformer under short circuit is similar to an induction motor with a black rotor. So, what is the black rotor? Here you can see what is telling that in our transformer. Okay. So, this is a winding, and second is a shorted with the thick one, SC test, OC test and SC test and transformers. Have you remember SC test, short circuit test. So, shorted secondary and given the some reduced voltage with the variac to this one. So, once it is short circuited, what will short circuit is a very high current will flows under this condition. We have to give the only some fraction of voltages only given to the rated voltage to the primary. Similarly, you can see the stator and given, and rotor bars are short circuited under running condition, because in squirrel cage what will happen, the bars already every time it is a short circuit at both ends. But whereas in case of the our slip ring rotors, what is shorted at the rheostats, rotor rheostats shorted fine under running condition. Okay. So, that is a short circuited, here short circuited, that is nothing but short circuited secondary of transformer. Our rotor also short circuited under running condition. Okay. Transformer under short circuit is similar to an induction motor with a blackwood rotor test. However, some differences are there in between the two. So, just we compare the what is the differences at a glance, you can see in table main basic differences. What is the difference? Here transformer and induction motor. First one is it is a transformer is a static device. What is that one? Transformer is a static device. There is no rotating parts in transformer. I can see here. It is a rotating device. Second one, here the coils winding is concentrated in transformers, whereas in this case distributed winding is used in stator and rotor. And here the magnetizing current is very less in case of our transformer. So, magnetizing current can be used to I naught. So, you remember that magnetizing current I0, that is equal to the vector of I mu plus I working components. So, this magnetizing current is a very low in case of transformers, whereas so magnetizing current is a high due to the air gap between the stator and the rotor conductors, and at the same time the high efficiency due to the low losses. There is no mechanical losses in our transformer, but here is a mechanical losses, friction and windage losses also extra in this case. So, low efficiency due to the high losses in induction motors. So, dear students, that is why its efficiency is a very high, above, that is a nearly greater than the 95%, whereas this efficiency is low. So, nearly that is a 90%, because losses are more in case of our induction motor, because it is a static, it is a dynamic. Okay. So, these are the some analysis between our transformer and our induction motor. Sir, what is the need up to this analysis, this much total analysis? Because if you know this analysis, because already we have drawn equivalent circuit of a transformer and equivalent diagram of the vectors under lagging power factor and the leading power factor, different loads also. Same analyze the in our induction motor also. Okay, that's why we require the some more basic idea to avoid any confusion. Okay, so it is a very easy if you know that basics. So that's why we recollected all things once again. Okay, let us do the equivalent circuit of our induction motor. Okay, so what is the induction motor? Now let us see equivalent. So up to we have compared these two machines. Now we are going to write it the equivalent circuit diagram of induction motor similar to our transformer. Okay, let us. So equivalent circuits. Equivalent circuit of an induction motor, the energy is transferred from stator to rotor is same as transformer operation, the induction principle. You can see this is one. The equivalent circuit enables the performance characteristics of induction motor and all for phase quantities is taken for simple analysis purpose here. Okay, so here, so what has happened? This stator winding and this is a rotor winding. So stator winding, what is the stator? This is the stator winding, and the stator winding has its winding. Okay, so this winding has some resistance, some inductance, that is the XL, and this rotor has its some resistance and some inductance. Okay, let us assume stator is a primary side, this is a R1 XL1, this is a R2 XL2. Okay, these are rotor parameters, this is a stator parameters. Okay, what is the R1 X1? The stator winding resistance and leakage reactance in ohms, whereas R2 and X2 we can say are the rotor winding resistance and leakage reactance in ohms at standstill condition. At this is a standstill, please remember that at standstill condition R2 X2. Under slip speed S is called some value, then so what will happen? The R2 is always R2R because the resistance doesn't depend on the frequency, whereas so what will happen? The X value, rotor reactance value, depend upon the frequency. What is the value? That is equal to, we can write it XL is equal to omega L. What is the omega L? 2 phi FL. So what will happen? The frequency under standstill condition of that is F2 is equal to S into F. That's the F2R is equal to S2 and F2. That means the rotor frequency developed under normal condition, that is equal to S is equal to 1 F2 only. At the rotor is running at a slip speed of S, then this rotor frequency is changed from F2 to S into F2. So if this value changes, we can say this FR2, that is called, we are going to substitute in this case, then the value of XL changes under running condition. Okay, so that means a standstill condition, the whatever the R2 X2 and under slip speed N speed, R2 is the same constant, does not change because it does not depend on the frequency, whereas the X2 changes based on the frequency values. So please remember that things. Okay, so rotor leakage reactance in ohms at a slip speed of S. Now at the same time, equivalent circuit diagrams we have seen that, so R0, what is the equivalent? The no load branch resistance, and it carries a working component. You remembered while you are drawing the I0 in transformer no load characteristics, so IW and I mu, okay, working component and I mu, and this is equal 50. So at the same time, you remember this is equal to, we can write it, this is equal to, so R0 and X0 values. Have you remember these things? So this is equal no load current I0. So I W and I mu. Okay, this is R0. What is the R0? No load branch resistance, and it carries working component of IW of no load current I0. And X0, what is X0? That is equal this value, that is called no load branch reactance, and it carries the magnetizing component current of I mu of no load current of I0. Okay, whereas the E1 and E2 are the stator induced EMF and rotor induced EMF and at slip S. Okay, these are the parameters. Same thing you can see. R1 X1 is the, what is the values? The stator winding resistance and leakage reactance in ohms. R2 X2 under rotor parameters, and X2 is the only rotor parameters under slip. So what is the R2? R2 is the same, and R0 and X0 both are the no load components, and E1 and E2 are the EMF induced in the stator and rotor due to the mutual induced EMF at standstill condition, at changing at the slip also. At S is equal 1, E2, and S is equal some value, that's E2 is equal to, that is ER2 is equal E2, S into E2. Okay. Now let us draw this one. So you can see the one figure. So this is a actual our induction motor stator and rotor. Okay. So what is the equivalent circuit diagram of transformer? Do you remember? Do you remember? What is the transformer equivalent circuit diagram? See here. Just you remember that. Okay. So this can be written as primary side, that is equal, it has a winding has some resistance, some reactance. Okay. So at the same time there is, we know that this is some components. This is the primary side, R1 X1 R0 X0. Okay. So this is we can apply the voltage V1, and induced voltage is equal to E1 here. Okay. Now this is the thing, and it is connected to the primary side. Similarly, this we are going to connect the secondary side, this side. So it has also winding, same I2. So we can write it, this current is okay. First we will write this value. It is also this one. It is this one. We are connected this one. This is equal to V2 and R2 X2 values. Okay, and induced voltage is equal to E2. This is the equivalent circuit diagram of transformer we have seen in previous classes. Okay. So what is the current values? The current values are, here, what is this one? This is called I1. So here the current is equal to I1. So I1 is equal to, we can write it. So here is the current is the I0. This is equal to I2 dash current, equivalent current. This is equal to I2. Okay. So this is the corresponding current, as you know that. So here I1 is equal to I0 vectors I0 plus I2 dash current. What is the reason? Already you know. So these are the current values, these are the voltage values. So V2 and V1 and E1 and E2. Here is R1 X1 R2 X2 values. Okay. These are the equivalent circuit diagram of single phase transformer for phase values. Similarly, I am going to write it same for our induction motor. Now what is the induction motor? Now I am going to this induction motor. Okay, it is a winding, 3-phase winding. You take the one phase. Okay, you take the one phase, for example R phase. So the winding has some resistance, and you can write it this winding. Similarly, So here is applied voltage. Now here is some resistance, some inductance similar to this one, and there is a magnetizing component. This is this one, and is connected here. Okay, so here what is the voltage applied? V1 is applied. This is R1 and X1, R0, X0, with I0 current. Okay, magnetic current. So this is equivalent to the this rotor circuit. This is a stator. Okay, this is stator, equivalent to stator. Now this is equivalent to stator. We can write it this is one stator. Now similarly we can write the rotor. So this is the rotor, taken out. So rotor circuit, also winding, and I am going to write it rotor circuit, also some resistance here, just like this is going to this one. Rotor has this one and this one. This is equal R2 and X2. Okay, so here this is the voltage induced. Now what is the this is equal to? So E2 voltage induced in this one, and the current is flowing this I2 under standstill condition. Suppose under running condition, you just multiply the S into S values. Okay, so this is the values in rotor. Rotor is short circuited. What are the induced voltage? E2, R2, X2. Under slip speed, S times you are going to multiply S into X2 here. Okay. Now in this case, what will happen? This is equal to E1, induced voltage E1. It's a rotor circuits. Now this is a similar to the stator equivalent circuit diagram. This is the rotor circuit diagram. Now combine it. What is happened here? Stator and rotor is placed. Then we are going to write it. This is similarly. So this is resistance, inductance, and components, and we are going to write it here. Okay, R1, X1, and the X0. We can take it this one. Okay, so this is equal to R0, X0. Okay, now we are going to write it. So some you can write the stator, this one. Okay, and this is the values, and I can remember represent with this current is equal to, I can write it that is called I1 current, and I can write it this voltage is called V1. I can write it this current is I0, and I can write it the IW working component. This is equal to I mu magnetizing component. Okay, and this voltage induced is equal to E1. Now write the secondary side. So secondary side you can write it. So another color you can take the another color. Now the secondary side you are going to collect the rotor circuit. You take the rotor circuit. Similarly, this is the resistance, this is inductance, and shorted here. This is called R2, X2, and here you are going to write it, that is called under S into E2 under slip speed. You can write it, it is also SX2. Okay, these are the equivalent circuit of our induction motor. Okay, so what is the here current is the I2 current. This current is the I2 current. Okay, stator current this one, and rotor current this one. Can I simplify this one? So yes, I can do it. So what is this one? So simply I can write it in equivalent circuit diagram. Okay, it's just you combining these two. These are the combining these two. I am going to get it. So what is this one? So I am going to get some thickness. You take it, and there is some resistance, inductance, and this is the magnetizing component, and this is the Now you can take it just like you write it the primary side, connect it. Okay, so this is the one. Similarly, in secondary side also take it, connect it and combine it. Okay, so these are the equivalent circuit diagram. Now represent the values. What is this value? This is equal to R1, this is equal to X1, this is equal to RW, this is sorry, you can write it the R0. Okay, you can write it R0, this is equal to X0. Okay, similarly you can write it, here is the R2 and you can write it the SX2 under S slip speed. These are the parameters. Now I am going to write it current values. Okay, what is the current values? This is equal to, you can write it V1 and this is equal to I1 and this is equal to, you can write it I0 and this can be write is the IW, this can I mu. Okay, I mu current, and this voltage induced is equal to E1. Okay, now in this case you can write it these values S into E2 at slip speed and here terms as N2, this is equal N1. Okay, N1 terms. These are the equivalent circuit diagram. Okay, from this one, so here this is a rotor, this is a rotor circuit, you can write it. So rotor, this is a rotor, this is a stator. Okay, now the rotor circuit further I am going to represent, this is a total electrical circuit only, but what we have seen, our rotor has developed electrical energy as well as a mechanical energy. Electrical energy in the form of heat energy, that is I square R winding losses, and remaining is the PM, the total mechanical power developed, PM, that is I am going to represent in the form of mechanical equivalent. So can I write it this equation into, so I can write it this equation, only rotor equation. So I can write it here, I can write it this equation with, so this equation I can write it in the form of SE2 and this is equal I2 current R2 SX2. Okay, I am going to write in the another form. Okay, so I can write this equation in the form of equivalent to resistance and reactance. This is I form this E2, this is called R2 by S and X2 and E2. I am going to write it. Okay, the equivalent circuit. So here whatever the S, I am just written the equations. So how we are going to change that one? So now, so how we are converted this one? We are converted. So we will see it now. So from this equation, I want to know that what is the current, total current I2. I want to know the value. I2 is equal to, the current in the circuit is equal to, so voltage by impedance. Okay, impedance value. Then what is the input voltage value? So voltage value is equal to this much, S into E2. What is the impedance? Root of R2 whole square plus SX2 whole square under root. Okay, this is the current I want to know. Now in this case, simple, it take out the S from this value. Then I can write it S E2 divided by under square of root. Okay, take the S outside. Then I can write it R2 by S square I am taken out. So divide by the all S2 R2 by S square plus X2 whole square. This is the value. I simply taken the S here common. Now I can get it S into E2 divided by S, we taken out the out root, then R2 by S whole square, okay, plus X2 whole square under root. Okay, S and S get cancelled. I am going to get it. What is the equation? That is equal to E2 by voltage by, what is the value? Can I write it? That is equal to R2 by S, okay, R2 by S plus J of X2. This is the equation. Simply I can write it this equation. Okay, so from this one I can write it. What is this one? The source. What is the impedance? This is equal to resistance. What is the inductance? This is equal to this one, and can write it the source. So this is equal to A2, and this is equal to, I can write it R2 by S. This can be, I can write it the X2. So simply I converted. What is the purpose to convert this one? I have some idea. So I want to convert this, whatever the rotor energy converted into the electrical energy as well as the mechanical energy. That purpose I am going to know this value. Okay. So anyone having any doubt? So this is current is equal I2. So same equation we can write it so here also with that one. So this equation, okay, we got it. From that I want to further analysis. So here the rotor circuit. So whatever the rotor circuit here, whatever the rotor, the stator and rotor, the rotor circuits further, the circuit is written as here, same circuit is written under slip speed. Now this rotor circuit further I want to convert it. It's because this is the electrical, this is the electrical. But I want the mechanical. Where is the mechanical energy output? I require the P out in the form of mechanical energy. So I want the mechanical energy in the form of electrical. I want to write it here. Okay. So because what is happened? So in the what is happened? What the rotor input is equal to rotor copper losses plus rotor mechanical energy developed. Okay, so here P2 rotor input is equal to, so whatever the rotor, this is equal to rotor input, you got it. Then this is a totally so mechanical. Where is the mechanical equivalent value? I want it. So then I am going to write this equation. So dear students, this is the P2 input power is equal to this one. At the same time, we know that equations we have written. What is that one? So I want the P copper loss of rotor. I can write it slips times of P2. Okay, so slips times, and P mechanical I can write it 1 minus S into P2. Already we have seen in previous classes. Now in this case the copper losses, can I write it? Because I know the copper losses in terms of current and resistance. Okay, so I want this value. So this value know the resistance and current. I know the current here, I know the resistance, I can know the what is the copper losses. So can I write it this one here? This can be write it in terms of current. And so I know the I2 whole square R. Here what is the R? R2 by S. This is the copper losses. Okay, so I can write it the copper losses is equal to I square R. Okay, so that is equal I square R. Simply you can write it here. So what is the copper losses? I square R losses. So here you write it. So this I square R is the copper losses, that is called PS2. Can you write it? The P2 can be converted. Here what is happened? P copper, once again you can see P copper losses is equal I square R losses is equal to S into P2. Okay, so here current is this one, R2 is this one. I want the P2. So P2 can I write it? What is that one? I2 whole square R2 by S. This is the one equation. Okay. Similarly, you can write PM also in terms of this value. Okay. So then what is the value PM also? We can write it. So here PM also you can write it. The PM is equal to 1 minus S into what is the P2? P2 is this value. Substitute I square R2 by S. Okay. So this is the second equation. Then write the equation in this value, with this in this one. Okay, in this one. What is this one? Once again, you write it. So P. We take the another color. Okay. Then P current, whatever the P2 is equal to, I can read it, P copper losses of rotor plus PM mechanical power generated. I am going to write it in terms of current and resistance. So I write it P2. What is the P2? P2 is equal I2 whole square and R2, okay, by S. And P copper loss I can write it I2 whole square R2, okay, plus PM I can write it, that is called I2 whole square R2 into 1 minus S divided by S. Same thing we written. Now what is happened? Here we take it. So I square and I square, take the common. Okay. Then we are going to this one. Okay. So what is the value we are going to get? So I square is common, taken out, and R2 taken out. Then what we are going to get here? 1 by S is equal to here 1. Okay, that is equal to, we are going to get 1. Just now you can see it. So these are the all equivalent circuit diagrams. So what just we have seen. Okay, axial rotor circuit. So the rotor circuit is simplified. Okay, so whatever this one value is simplified into this value by just dividing by the S in the equation. Okay, so what is this current? Current equation, I is equal to voltage by impedance. Okay, so what is the voltage? That is equal to S into E2. What is the impedance? These two values, this value, R2 whole square plus SX2 whole square under root. Now I taken the S outside. So then because I require the S to cancel, then I am going to get that. So E2 by R2 by X whole square plus X. So yes, we are going to S X2 whole square under root. So, this is written in the form of this equation, E2 is equal to this one and this values. Okay. Now, here rotor input P2, so similarly written as these two values. The rotor input is equal to power loss in the circuit and mechanical equivalent circuit. So, we written this form. So, this whatever the value here we taken, this is equal to this value, I can write in terms of R2 plus RL, that we can write the RL equivalent rotor circuit. What is that one? So, here I have written, this is the equivalent circuit diagram. So, this is the value. Okay. Now, so total rotor side parameters transform to the primary side as just we have seen. Then finally, we are going to the these values in primary side, and further we simplified this into this equation. This is the final equivalent induction motor circuit diagram. Okay. So, just we have seen. Now, let us draw the one vector diagram. Lastly, based on these components, we are going to draw the vector diagram. The behavior of an induction motor is similar to that of the transformer. The vector or phasor diagram between the two similar values. The phasor diagram is drawn on a for phase basis. So, the mutual flux between the stator and rotor winding as reference phasor. Here taken the reference values are taken this one. And this flux includes the EMF in the stator and rotor, and EMF under the running conditions E1 and SE2 respectively, lagged by the phi angle by the 90 degrees. Okay, you can draw that equivalent diagram. So, better to equivalent diagram. Now, so here take the what is set one value, we take the reference value. Okay, then this is another value. Here I taken the that is called phi reference, and this side I taken as a V1 applied voltage, and correspondingly induced voltages are this side, that is equal to E1 and E2. Okay, this both side, and whereas E2 is equal to ER is equal to S into U2, I can write it for simplification. Now, in this circuit, what is happened? Based on the circuit, you can take the circuit also. So, what we are going to write it? So, here we can write it. Okay. So, what is the circuit? Just this circuit is equal to stator and rotor. Okay, R2 SX2. This induced EMF is equal to SE2, rotor under slip speed. This is equal to I2 current. Okay, this current is equal to I1 and this is I0. Okay, now this is equal to induced voltage across this was equal to E1, applied voltage is equal to V1. Okay, so I am going to calculate these values in terms of all parameters. Now, what is happened in primary side? Now the current I0 taken as a no load current, this is called I0, and I0 has two components. One is a working component, that is a IW, this is called I mu, similar to the our transformers. Okay, this is working component, this is the magnetizing component of current, no load current. Now in this case, this is a current. Now I want to know the primary current, so I want to know the secondary current also, I2 current. So due to the inductance effect, here whatever the voltage, this voltage lagged by the some current of I2. So E1 is this one, E2 is this one, and the current which is taken as you can take another, this is equal to I2, this is equal, you can write it the I2 current, and this I2 current is taken as some angle, this is equal to I2 current dash, I2 dash. Now resultant of this current, I am going to get the resultant current, that is equal to I1 current. Okay, the current is the I1 current, we got it from the this I0 and I2 current. This current I2 dash current. Now based on the I1 current, the primary side, what are the primary side values? I1 current, I1 into R1, I1 into X1. So I am going to write it here. This is voltage V1 voltage, and induced voltage E1, so that is equivalent to the this E1. So I can write it in terms of minus V1, some angle, the reverse taken this E1 in the form of this value. Okay, so then E1 we taken some angle here, this is equal E1 induced voltage here, this is E1, and this drop. So this E1, what is the current value? This angle, current value is this angle, perpendicular. Then we are going to get it. Okay, so perpendicular value, you can write it. Then this is equal to I1 R1, I1 X1, combined it. So we are going to that. So Z. Then we are going to that it. So V1, we can write it, this is equal to V1. Okay, V1 is equal to, we can write it I1, Z1 and I1. So we are going to this value and this primary side. Now coming to the secondary side, here what is the secondary side? This current. So I2 dash is this one, and then this is a drop E2 and this one. So this D2 is equal this drop plus this drop, I am going to write it. Then so I am going to this I2 in the same direction, that is equal to, I can write it in the form of the color. So this is equal to, I can write it, that is equal to, so I2 R2. Okay, now this is equal to I2 X2, and this is equal to E2. Okay, so I can write the SE2. So this is the secondary side and this is the primary side, this value. This is a phasor diagram. You know the phasor diagram, how to draw this phasor diagram. Okay, so dear students, don't confuse it and practice it. Okay, can you write it? And otherwise I can write once again. So once again I can going to write it. Please see, based on this diagram, I am going to write it once again, you can see it. So take the whatever the values. So here this is the one diagram. Take the reference, this is the reference, and take the I0 as per phi angle, phi naught, we take the I0 value, and based on this one you can say it, this is called I0, and I working component, I mu components. Okay, this is over, I naught is over. Now I want the I1 current. I1 current is the I0 plus the magnetic current, the I2 dash current is required. So because due to the lagging I2 current in the secondary circuit, the current is flowing, this is we taken the E2, we taken this is the S into E2, this is a voltage. The current always lagged by some angle. This is some angle. This is the we taken the I2 dash, I2 current. SE2 voltage, this is current, some angle is the phi 2. Similarly, extend these values in this direction. Can I write it minus I2? This is equal minus I2, or we can write the I2 dash minus I2, or I can write it the I2 dash. Now you know that this current, this current, so you are going to write that. So resultant of this value, you are going to get it. That resultant value is nothing but I1. Okay, so I1 current, this is the I1 current. Now here V1 is also induced in the, this is called E1, induced in the self-induced EMF. So that is the total V is equal to this drop plus this E1. Now E1 is this direction because always opposite to the V1. Now we take the that side. So that is equal, you can take the some angle is lag E1. Then current, so this current I1, this is current I1 R1, this is 90 degrees, this is called I2 X2, this is a I1R. Then you can write the, this is a Z. Then so we are going to get this is called V1. Okay, it is same just like this V1 is going to this one. And similarly, so take this I2 we know, and I1 same phase, I2 R2 90 degrees, I2 X2, and this is equal to SC2. So this is the secondary side, this is the primary side. Okay, so just you practice it. So here it is difficult to write this a small area. Now same thing you can see here. So this is the diagram. So this phi is written, and IW working components, all things magnetic component, I mu, that is I0, this is the components E1, and this is a E2, this current I2 dash, current component, and I2 R2 dash, all this of phi 2, I2 dash is the reverse, and this is the resultant of I0 plus I2 dash is equal, we are going to the I1, and this is called V1, we are going to write it, and this is E1, that is called induced EMF in the opposite direction, and this is I1 R1 in the same direction of I1 current, and I1 and R2 is 90 degrees to this one, and we are going to the I1 X1, and we are going to the I1 Z1 represented value. Okay, so here the vector sum of E1 plus I1 R1 plus I1 X1, we are going to these values. Okay, this is the vector diagram. And coming to the secondary side, this is called I1 I2 R2 and I2 X2, and E1 we are going to get it. Okay, so similar this diagram, you can see this analysis. This is the diagram, original diagram, you can see it. Okay, so how we are going to written these equations, all already you know. The voltage SE2 is set up, the rotor current I2 lagged by some angle due to the inductance effect. So we can calculate phi 2, that is the tan inverse of SE2 by R2, and SE2 is equal to the rotor impedance drop. Okay, so these are all equations. What is the angle? Once you written this diagram, you are going to calculate what is the all values in a diagram. Okay, cos phi 1 is the power factor towards the stator, and cos phi 2 is the second side. What is that value? So here you written that is equal to I1, this is equal to I1, this is equal to I2. So correspond this phi 2, this is equal to, you are going to get it phi 1. Okay, and v1 is equal to, so vector sum of this e1 plus this one. So what are the value we got it? So this side, so you are going to get it, and this is equal to e, you are going to e1, this is you are going to get the v1. So this is e1, this is called I1 R1 I1 x1. So this plus this, that is equal, you are going to get the v1. Okay. Now let us summarize what we have seen in this class. So explanation with a circuit diagram how an induction motor is treated as a generalized transformer, and how to draw the equivalent circuit as referred to the stator, and how to draw the vector diagram with the phasor diagrams. Dear students, so it is a very lengthy, but so you have to just the very simple diagrams. Whatever you are compared with our transformers, if you have the basic idea on transformers, equivalent circuit diagram and vector diagram, it is a very easy to write here only. Only in that case there is a slip, in this case only slip is present. Under standstill condition the slip is equal to 1, but it is a running condition, only the terms included in S. Okay. So this is the overall idea of equivalent circuit diagram induction motors. So just you practice it. Okay. Thank you for listening my class.